Okay, welcome back. So I'm going to do a short video. So this is the next part, which is going to be about, it's going to be the last part dealing with the difference of means, and it's going to handle the topic or the situation where, what if you're given the information that the variances of the populations are equal, okay? And this is where we're going to use a pooled variance. And this is where on the calculator that we discussed before, where you're going to talk about pooling. Well, if we assume that the population variances are equal, then what we can do is we can take the two samples and pool them together and use them as like one large sample with a common variance. And so what we're going to end up doing is sort of like averaging the variances of both populations to come up with a common variance for the pooled data. Okay, and so that's the idea. So how do we calculate this pooled variance? I'm going to show you in a moment. But on the calculator, you would just choose pooled, yes. Okay, so if you're given in the problem, so again, this is a t-distribution. This is under doing a t-test, the two-sample t-test. If you don't know what the population the population standard deviations are, okay, and you're given in the problem that to assume that the population variances are the same. Or if you are given that, but you look at the sample standard deviations or the sample variances and those are the same, then you can assume that the population variances are also the same. So either you're going to be told in the problem to assume that the variances are the same for the population, or you'll notice that the sample variances or the sample standard deviations are exactly the same, and in that case, you can assume it, okay? But other than that, if you're in doubt, just don't pool, okay? But in this example that I'm going to do, we're going to make the assumption that the variances are the same for the populations, and we're going to act accordingly, okay? So let me show you what I mean by the pooled variance, and I'm going to use the standard error that we showed last time. So remember, the standard error was this calculation here, right? It was S1 squared over N1 plus S2 squared over N2, right? And we called this the standard error. Well, what happens if we assume the population variances are indeed the same? Then what we can do is, again, like I said, we could pool the samples together and calculate a pooled variance and then use that variance for both samples. So basically treat both samples as one, okay, and get a common variance, or on what we call the common sample, you could say, okay? So how does that work? Well, the calculation for the pooled variance is this. And we use it as S sub p squared. Okay. The calculation is going to be this. We take the degrees of freedom of the first sample, N1 minus 1, multiply it by the variance of the first sample. So that's going to be S1 squared. And then we add it to the degrees of freedom of the second sample times the variance, the sample variance of the second sample. So in the numerator we get this product plus this product. So we take the degrees of freedom of the first sample times the sample variance of the first sample. And then we take the degrees of freedom of the second sample and we multiply it by the sample variance of the second sample. And then we take those two products and add them. And then the denominator is just the sum of the degrees of freedom for both samples. So it's just going to be N1 minus 1 plus N2 minus 1. And if you simplify it, it just becomes N1 plus N2 minus 2. And so this calculation becomes the formula for the pooled variance. So now, What happens to our standard error then? Well, we don't use this one because now what we're going to do is we're going to replace both of these with this, S of P. Okay? So what happens is, this is what we get. Okay? And so again, this is if we assume, let me do this. Okay? So that the population variances are equal. So now if we're going to use this as our pooled variance, and we're going to replace both of the sample variances with the S of P. And now what happens is now we can simplify this even further, and we can pull the SP squared out of the radical and then take the square root of it and simplify it. So what happens is this becomes S sub P times the square root of 1 over N1 plus 1 over N2. And the degrees of freedom, now here's the thing. The degrees of freedom is really easy if you're using the pooled variance. If the population variances are the same, then the degrees of freedom just becomes the sum of the degrees of freedom for both samples. So this actually just becomes the degrees of freedom. So the degrees of freedom is just N1 plus N2 minus 2. Okay? Much easier than that other formula we had to look at, right? So if the data is pooled, or excuse me, if the variances are the same, if the population variances are the same, then we can pool the variances and use this in replace of both variances and then simplify it to this standard error. So the standard error becomes this instead of what we were using before. And so now what happens is, okay, is this. Our t statistic, t star, now becomes this. X bar 1 minus X bar 2 minus the quantity mu 1 minus mu 2 divided by now this. S sub P times 1 over N1 plus 1 over N2 square rooted. And so now this becomes the calculation for our test statistic. Okay? And again, you don't have to do this because this, all this means is you just have to use, when you, on the calculator, on the 2-sample t-test, when it gets to the question of pooled or not, yes or no, pooled, in this case here, you would say yes. Okay? So let's do an example. And then we'll move on. So the example I want to use is this one. A study is done to determine if Company A retains its workers longer than Company B. Company A samples 15 workers, and their average time with the company is 5 years with a standard deviation of 1.2 years. Company B samples 20 workers, and their average time with the company is 4.5 years with a standard deviation of 0.8. The populations are normally distributed. So now, so here, we don't know the population standard deviations, and what we're going to do is we're going to assume that they're the same. Okay, so we don't know what they're at, we don't know what they are, but we're going to assume that the standard deviations are the variances, the population variances are equal. Okay, so it's going to be a t-distribution where we're going to use the pooled variance. Okay, so let's set up our hypotheses. And so what do we have? Well, first we have to determine what is going to be population 1 and what's going to be population 2. So population 1, let's make that Company A, and let's say population 2, Company B. Okay. Now that we know that, let's look at the claim. The claim is that company A retains its workers longer than company B on average. So that would mean that mu1 is greater than mu2. So that's going to be mu1 is greater than mu2, and that's the claim. So that's what we're testing. So that means the null is mu1 is less than or equal to mu2. And so now we're off. So we're out of the gate now. So again, we're going to assume mu1 is equal to mu2. In other words, mu1 minus mu2 is equal to 0. And now step 3 is we're going to write down the information. Our, where is it? The alpha level is 0.05. They don't give us an alpha level, so we always use alpha equal to 0.05 if it's not stated. So now, what do they give us? So let's do our population. Let's give our information. So there's A and there's B. So this is 1, this is 2. So for A, they sample 15 workers. So N1 equals 15. Their average time, so X bar 1 is equal to 5. And their standard deviation, S1, is 1.2. So these are in years. And then for company B, their sample was 20. So N2 equals 20. X bar 2 equals 4.5. And S2 equals 0.8. So 0.8. Now, we are asked to assume. So we are going to assume that sigma 1 squared is equal to sigma 2 squared. Now, we don't know sigma 1 and sigma 2. So sigma 1 and sigma 2 are unknown, right? If we knew what they were, we wouldn't have to assume that they're equal, right? We would know that they're equal or not equal. So that's why this only makes sense that if we're using a t distribution, okay? So sigma 1 and sigma 2 are unknown, okay? So now we're going to use the t distribution. So we're going to use 2 sample t test. And now, once I go to the calculator, here's what I'm going to do. So I'm going to go to stat tests, 2 sample t-test, and now I'm going to use statistics again. Okay. Now, note that I haven't done anything with data. Okay. But understand that if you're given data, you would be given data for 2 samples. Okay. And what you would do is you would have to put the data for the first sample into one list, put the data for the second sample into the second list, and then basically for the 2 sample z-test or the 2 sample z-test, you would just tell the calculator where are your 2 lists, and the calculator will ask you where are your lists located, and you'll have to say, well, this list is in L1 and this list is in L2, or wherever you have your data at, okay? And then basically you just plug in the information that they're looking for and then hit enter. So that's the only difference between doing the stats versus the data, okay? So just practice using, there's examples in the textbook where they give you data. Practice entering the data so that you know how to do it, okay? Because that is something you could be asked for on the exam, okay? If it's not done in class, okay? So anyway, they give us stats. So again, we're going to use the stat option for the input. So stat, now X bar 1 is 5, S1 is 1.2, N1 is 15, X bar 2 is 4.5, S2 is 0.8, N2 is 20. And the alternative hypothesis, our test is greater than, so we're choose greater than. Now, pooled. Pooled is yes, because we're assuming the variances for the population are equal. Therefore, we're going to choose yes this time. And now we're going to hit calculate, and this is what we get. So now, the t statistic, our test statistic is 1.479. 1.479. Our p-value equals 0.0743. 0.0743. Okay, now guess what the degrees of freedom are? The calculator tells us the degrees of freedom are 33. Well, how do they get that? Well, you take the degrees of freedom of the first sample and the degrees of freedom of the second sample and add them together. So you get 14 and 19 give you 33. So in other words, 15 plus 20 minus 2 is 33. There you go. So there's the proof in the pudding. Okay. So now step 5 is, well, what comparison do you want to make? Let's do the p-value method. So p-value, which is equal to 0.0743, alpha is equal to 0.05, and is our alpha less than, or excuse me, sorry, is our p-value less than alpha? No, it's not. So what does that mean? Well, if our p-value is less than alpha, we reject. Then that means that if our p-value is not less than alpha, we fail to reject, right? So we fail to reject. And so now the conclusion is well, we would go back to the claim. So if we fail to reject the null, does that mean that there's enough evidence to support the alternative? No. And in this case, the alternative is the claim, so there's not enough evidence to support the claim. So at an alpha level of 0.05, there's not enough evidence to support the claim that the average number of years that an employee stays with company A is greater than the average number of years that an employee stays with company B, based on the sample data. That's it. Okay, guys, that's all I have to say about the difference of means. So we've covered everything that we could do for a difference of means. And so next time, we're going to talk about how do we handle how do we test for the difference in population proportions. So I'll see you next time.